Welcome travelers to Adventures in Security. In this video, we explore distributed applications, related cybersecurity challenges, and how to meet those challenges. The research paper on which this video is based is available in the video description. If you like what you see, if you learn anything, be sure to subscribe so you don't miss future content. The advent of distributed applications has reshaped digital infrastructure, particularly as decentralized technologies such as blockchain gain traction across critical sectors. These applications operate over interconnected systems, eliminating centralized control points to enhance fault tolerance, scalability, and resilience. In contexts such as decentralized finance, DeFi, and smart energy grids, DApps facilitate autonomous transaction processing and distributed resource management. However, the distributed nature of these applications also makes traditional security models inadequate. Cybersecurity challenges manifest in various forms, from expanded attack vectors arising from the proliferation of microservices and APIs, to the immutability of smart contracts that hinders incident recovery. As DApps become integral to mission-critical operations, there's an urgent need to understand their unique threat landscape and develop security paradigms that can effectively mitigate risks without undermining decentralization. This paper analyzes DApp vulnerabilities in depth and presents mitigation strategies grounded in recent research and regulatory guidance. Distributed applications, DApps, are software systems that operate across multiple networked computers, enabling resource sharing, scalability, and fault tolerance. These applications are integral to various sectors, including financial services and energy systems, where they facilitate complex, decentralized operations. In the financial sector, distributed applications are exemplified by blockchain-based decentralized finance platforms, allowing for peer-to-peer financial transactions without traditional intermediaries, enhancing transparency and reducing costs. For instance, DeFi applications enable users to lend, borrow, and trade assets directly, leveraging smart contracts to automate and secure transactions. In the energy sector, distributed applications, such as solar panels and wind turbines, manage distributed energy resources. Blockchain technology facilitates the integration and coordination of these resources by providing a secure, transparent ledger for energy transactions. This approach enhances grid resilience and allows for more efficient energy distribution. Redundancy and replication strategies achieve distributed applications fault tolerance. Distributing data and processes across multiple nodes allows the system to operate smoothly even if individual components fail. This resilience is crucial for maintaining system reliability and availability. These strategies are commonly achieved by using the Interplanetary File System, IPFS. The decentralized nature of distributed applications introduces several cybersecurity vulnerabilities. Attack surface expansion, data consistency and integrity, authentication and authorization, and incident response complexity. The expansion of the attack surface in distributed applications presents significant cybersecurity challenges due to the increased complexity and number of components within modern software architectures. Distributed applications rely on interconnected microservices, APIs, and often hybrid infrastructure, which creates numerous entry points for adversaries. Each microservice may expose unique vulnerabilities, especially when there is a lack of standardized security practices across services. As these services communicate over networks, often using REST or gRPC APIs, they may be susceptible to attacks such as injection, spoofing, and man-in-the-middle if not properly secured. Application programming interfaces, APIs, essential for inter-process communication in distributed systems, substantially broaden the attack surface. NIST emphasizes that the API lifecycle, including design, deployment, and deprecation, must include strong authentication, authorization, encryption, and input validation controls to reduce risk. Further, the decentralized nature of distributed systems undermines perimeter-based security models, making identity and access management (IAM), zero trust architecture (ZITA), and continuous monitoring critical strategies for risk mitigation. Integration with operational technology (OT) and Internet of Things. IoT systems introduces additional vectors, particularly where legacy systems are involved. NIST's guidance on OT security recommends network segmentation, strong device identity, and protocol-aware intrusion detection as essential practices in these hybrid environments. Advanced persistent threats. APTs often exploit such complex, loosely governed environments. Research shows that incorporating artificial intelligence, AI and machine learning, ML, into security operations centers, SOCs, can reduce response time by detecting anomalous behaviors and correlating telemetry across distributed nodes. These technologies enable proactive threat hunting and support dynamic risk scoring, essential for securing modern distributed applications. The asynchronous operations across distributed nodes complicate data consistency in DApps. Unlike centralized systems where a single source of truth exists, DApps rely on consensus mechanisms to validate transactions, which can lead to temporary inconsistencies. For instance, integrating off-chain storage solutions, such as caching mechanisms, can introduce synchronization issues. A study by Liu et al. Proposed a blockchain node-based distributed caching architecture to address real-time responsiveness in DApps. While this approach enhances performance, it also necessitates robust mechanisms to ensure that cached data remains consistent with the blockchain state. Blockchain's immutable ledger inherently supports data integrity in DApps. However, challenges arise when integrating with external systems or when user interfaces do not accurately reflect the underlying smart contract logic. Young et al. Highlighted discrepancies between front-end representations and innovative contract implementations in DApps, leading to potential user mistrust. Furthermore, the NIST has addressed the importance of access control in decentralized systems. NIST's guidelines underscore the necessity of implementing robust access control policies to prevent unauthorized data manipulation, which is crucial for maintaining data integrity in DApps. Traditional authentication methods, such as username and password combinations, are ill-suited for DApps. Instead, DApps often utilize wallet-based authentication, where users sign transactions using private keys stored in digital wallets like MetaMask. While this approach enhances security by eliminating centralized credential storage, it introduces usability issues. Users unfamiliar with blockchain technology may find managing private keys and understanding wallet interactions daunting, leading to potential security lapses or application abandonment. Moreover, the lack of standardized authentication protocols across DApps and blockchain platforms exacerbates the problem. Now, this fragmentation can result in inconsistent user experiences and complicate the development of interoperable authentication solutions. NIST guidelines emphasize the importance of implementing robust authentication mechanisms, including multi-factor authentication and secure key management, to mitigate these challenges. Authorization in DApps is typically managed through smart contracts, which define access controls and permissions. However, coding errors or vulnerabilities in smart contracts can lead to unauthorized access or privilege escalation. The immutable nature of blockchain means that once a smart contract is deployed, correcting such issues is non-trivial and may require deploying new contracts and migrating users, which is both time-consuming and risky. Additionally, the decentralized nature of DApps complicates the implementation of traditional access control models. NIST's research on blockchain for access control systems highlights the need for tamper-evident decentralized authorization mechanisms that support dynamic policy updates. Implementing such systems requires careful design to balance security, scalability, and user privacy. DApps introduce a host of incident response complexities that challenge traditional cybersecurity protocols. One core issue lies in the immutability of smart contracts. Once deployed to a blockchain, smart contracts cannot be altered without significant procedural overhead, often requiring complete redeployment or use of proxy patterns, which not all DApps implement. This immutability hinders rapid patching of discovered vulnerabilities, leaving systems exposed even after an exploit is identified. The inability to hotfix contract logic increases the time window available to attackers, as highlighted in the exploitation of reentrancy vulnerabilities and flash loan attacks. Furthermore, the decentralized and pseudonymous nature of DApp ecosystems impedes attribution and containment. Unlike centralized systems where user identities and system activities are logged within enterprise infrastructure, DApps often operate on permissionless blockchains, where user activity is linked only to wallet addresses. This complicates forensic analysis and coordination during incident response, especially when malicious actors leverage privacy-enhancing tools or cross-chain bridges. Another challenge is the absence of centralized governance. Incident response in traditional systems benefits from clear roles, responsibilities, and escalation paths. In contrast, DApps rely on decentralized governance mechanisms, such as decentralized autonomous organizations, DAOs, which may require community consensus to act, delaying response times. In time-sensitive attacks, this delay can exacerbate losses or security failures. NIST's guidance on cyber resilience underscores the importance of rapid containment and recovery, objectives that are difficult to achieve in decentralized settings, where coordination spans multiple anonymous stakeholders and platforms. Finally, interoperability among blockchain networks further complicates incident response. Many DApps engage in cross-chain operations, making them susceptible to exploits propagated across platforms. This introduces the need for multi-chain monitoring and coordinated response strategies across heterogeneous trust environments. To address these challenges, several strategies have been proposed. Implementation of security frameworks, secure communication protocols, regular security assessments, incident response planning, zero trust architecture, and IPFS and ephemeral certificates. Implementing security frameworks in DApps is crucial to addressing the unique challenges posed by their distributed and immutable nature. Traditional security models often fall short in this context, necessitating specialized frameworks tailored to DApps' specific needs. One such framework is the Ethereum Security Analysis Framework, ESAF, designed to analyze smart contracts for vulnerabilities. ESAF integrates static and dynamic analysis tools to detect common issues like reentrancy attacks and integer overflows, providing developers with insights to enhance contract security. The NIST has also contributed to developing security frameworks for blockchain applications. NIST guidelines emphasize integrating security measures throughout a DApp's lifecycle, including secure coding practices, regular audits, and incident response planning. Secure communication protocols are essential for DApps to ensure confidentiality, integrity, and authentication in a trustless environment. Unlike traditional applications, DApps operate on decentralized networks, necessitating innovative approaches to secure communication. One prominent protocol is the DMail messaging protocol, which facilitates secure communication across various networks by leveraging Web3 identities, such as decentralized identifiers, DIDs, NFT domains, and wallet addresses. This protocol enables seamless interaction between smart contracts and decentralized applications, ensuring encrypted and authenticated messaging without relying on centralized servers. Another significant development is the sending network, which addresses the need for secure, scalable, and efficient messaging in decentralized environments. It employs the double ratchet algorithm for end-to-end encryption and introduces a delegation scheme to optimize message processing in large group chats. Additionally, it incorporates proof of relay and proof of availability consensus mechanisms to validate message relay workloads and ensure network consistency. The NEOM MixNet offers a privacy-centric solution by anonymizing metadata and obscuring traffic patterns. It utilizes layered encryption and a series of mixed nodes to route messages, making it difficult for adversaries to perform traffic analysis. NIM's approach enhances user privacy and is particularly beneficial for applications requiring high levels of anonymity. Furthermore, the Quark's messaging network integrates blockchain technology to provide a secure and decentralized communication platform, ensuring message confidentiality and integrity through cryptographic techniques and eliminating centralized control, thereby enhancing resistance to censorship and unauthorized access. Regular security assessments are vital for maintaining the integrity and resilience of DApps. Given blockchain's immutable nature and smart contracts' autonomous operation, identifying and mitigating vulnerabilities before deployment is paramount. Encompassing on-chain components such as smart contracts and off-chain elements, including APIs, web interfaces, and cloud infrastructures. Comprehensive approach to DApp security involves integrating formal verification techniques, static and dynamic code analysis, and adherence to established security frameworks. For instance, Saxena emphasizes the importance of employing formal methods and code analysis tools to detect and rectify potential vulnerabilities during development. This proactive strategy ensures security is embedded into the DApp's architecture from the outset. While not exclusively tailored for DApps, the NIST provides guidelines that offer valuable insights applicable to their security assessments. NIST Special Publication 800-228 outlines best practices for API protection, which is particularly relevant for DApps that rely on APIs for off-chain interactions. Implementing these guidelines can help identify risk factors and establish controls to safeguard against potential threats. Furthermore, real-world case studies highlight the necessity of regular security evaluations. For example, the security assessment of Singularity DAO's DApp involved stress testing its AWS cloud architecture and adopting new security measures to fortify its infrastructure, aiming to identify potential risk areas and provide recommendations for enhancing the platform's security posture. Incident response planning for DApps presents unique challenges due to their distributed architecture, immutable smart contracts, and often pseudonymous user interactions. Traditional incident response frameworks must be adapted to address these specific characteristics. The foundational aspect of incident response planning involves clearly defining what constitutes a security incident within the context of DApps. This includes scenarios such as unauthorized access to smart contracts, exploitation of vulnerabilities, and anomalies in transaction patterns. Establishing clear criteria ensures teams promptly recognize and respond to potential threats. The NIST provides a comprehensive framework for incident response, which, while initially designed for traditional IT systems, offers valuable guidance applicable to DApps. NIST's incident response lifecycle comprises 4 phases: preparation, detection and analysis, containment, eradication, and recovery, and post-incident activity. Adapting these phases to the decentralized nature of DApps involves coordinating with decentralized governance structures and managing immutable code bases. Preparation involves establishing an incident response team with clearly defined roles and responsibilities, tailored to the decentralized environment. This may include smart contract developers, security analysts, and community representatives. Detection and analysis require continuous monitoring of on-chain activities and off-chain components to identify anomalies indicative of security incidents. Given the transparency of blockchain transactions, leveraging real-time analytics can enhance detection capabilities. The immutable nature of smart contracts complicates containment, eradication, and recovery in DApps. Once deployed, smart contracts cannot be altered, making it challenging to address vulnerabilities post-deployment. Implementing upgradable contract patterns or proxy contracts can provide a mechanism for updates while maintaining the integrity of the blockchain. Zero Trust Architecture, ZTA, is a cybersecurity model that operates on the principle of never trust, always verify, ensuring that no user or device is granted access without thorough authentication and authorization. In the context of DApps, implementing ZTA presents unique challenges and opportunities due to the inherent characteristics of blockchain technology. Traditional ZTA models, as outlined in NIST Special Publication 800-207, emphasize continuous verification, least privilege access, and the assumption of breach to protect organizational assets. These principles are particularly relevant for DApps, which operate in decentralized environments without centralized control, making traditional perimeter-based security models ineffective. Recent advancements have focused on adapting ZTA principles to cloud-native and decentralized environments. NIST Special Publication 800-207A provides a model for access control in cloud-native applications, emphasizing the need for dynamic policy enforcement and continuous monitoring in distributed systems. This approach aligns with the operational dynamics of DApps, where components are often distributed across various nodes and networks. In the realm of DApps, implementing ZTA involves integrating decentralized identity management, leveraging blockchain's inherent transparency and immutability for audit trails, and employing smart contracts for automated access control. For instance, the Zonia system introduces a zero-trust Oracle network for IoT applications, utilizing blockchain to ensure data integrity and trustworthiness in decentralized environments. Furthermore, combining ZTA with blockchain-based federated learning and anomaly detection frameworks enhances security in decentralized systems. Such integration allows for secure collaboration among distributed nodes while maintaining strict access controls and continuous monitoring, essential components of ZTA. Integrating the Interplanetary File System, IPFS, with ephemeral certificates offers a promising approach to enhancing security and privacy in DApps. IPFS provides a decentralized content-addressable storage system, facilitating efficient and tamper-resistant data distribution across a peer-to-peer network. Ephemeral certificates, characterized by their short-lived validity, serve as temporary authentication credentials, reducing the risk associated with long-term key exposure. Incorporating ephemeral certificates into DApps utilizing IPFS can bolster security by ensuring that access credentials are valid only for a limited duration, minimizing the attack surface. This approach aligns with the principles of zero-trust architecture, where continuous verification is essential and no entity is inherently trusted. For instance, in scenarios where sensitive data is stored off-chain in IPFS, ephemeral certificates can grant time-bound access to authorized users, ensuring that even if credentials are compromised, their utility is temporally limited. Moreover, using ephemeral certificates can facilitate compliance with data protection regulations by enabling fine-grained access control and auditability. By issuing certificates with specific scopes and lifespans, DApps can enforce strict access policies and maintain detailed logs of data access events, thereby enhancing transparency and accountability. This is particularly relevant in applications involving sensitive information such as digital identity management and secure communications. While integrating ephemeral certificates into IPFS-based DApps offers significant security benefits, it also introduces challenges, such as the need for robust certificate issuance and revocation mechanisms. Ensuring the timely distribution and validation of certificates requires a reliable and scalable infrastructure, which may necessitate additional development and operational efforts. Furthermore, the decentralized nature of IPFS may complicate the implementation of traditional certificate revocation methods, necessitating innovative solutions tailored to distributed environments. That's it for this video. If you have questions or comments, post those in the video discussion. And until next time, be careful what you click.